were you born in Russia?
Sorry?
Were you born in Russia or no?
Yeah,
Where, if I can ask?
Moscow.
Oh, Moscow. So maybe we can gradually start. I think people might join in and also watch live on, if that's okay. And so, uh, welcome everyone. Welcome to Harvard CMSA Quantum Math in Math and Physics seminar series. Today, it is my great pleasure and honor to introduce Professor Max Metlitski from MIT. And I think Max is already famous enough, not requiring introduction. But I would like to say it's great that he giving a talk again. Although the topic is similar or the same, but I hope that the audience can interrupt and ask questions, so the outcome might be different. And today he will be speaking about boundary criticality of the OL model in D=3, and criticality revisited. And so audience, again, please welcome to interrupt and ask questions. And let's welcome Max.
Thank you, Jovan, for the invitation and the kind introduction. Yeah, I don't think I spoke about this particular subject at CMSA, but many people in the audience might have heard this talk in some form already. If you heard it something like a year ago, then the difference might be that I'll talk about some numerical work that has appeared since then, which I think is quite interesting. Yeah, so I'd like to talk about boundary criticality, and this is an old subject with a history going back to classical statistical mechanics in the 70s and 80s. But I'd like to convince you that actually some very basic cognitive issues have been missed back then. Okay, so what is boundary criticality? Boundary criticality is a study of critical systems, right? So we have a bulk system that's tuned to a critical point. To be precise, let's assume that this critical point is described by a conformal field theory, and we'd like to study the properties of this system in the presence of a boundary. So, for instance, we might like to study correlation functions involving operators both in the bulk and on the boundary. And there are a few comments that one must immediately make about this problem. First is that the physics near the boundary in general is different from the physics in the bulk. For instance, the spectrum of boundary operators is distinct from the spectrum in the bulk. For instance, the boundary operators have in general scaling dimensions that differ from the scaling dimensions in the bulk. So this is the first point. The second point is that the boundary conformal field theory corresponding to a given bulk conformal field theory is not unique. There can be multiple boundary universality classes corresponding to the same bulk universality class. And you can tune between these boundary universality classes by changing the microscopic Hamiltonian near the boundary. And we will see some examples of this. So kind of loosely speaking, there can be more than a single boundary condition. As I said, this problem of
Max, maybe I can. I'm sorry to interrupt too early, but still, I'm trying to because it's kind of more generic, right? I wonder. Let's say that you have this box or whatever, right? Then my kind of intuitive feeling would be that I can put a very much different boundary condition, let's say, and still think that this bulk, say, anomalous dimension would be the same. It is still true, right? Or it's not true?
It's correct. So there are several kind of universal properties. So first property is bulk correlation functions. So if you go very far away from the boundary, what are the bulk correlation functions? In particular, what are the bulk scaling dimensions? And
Yeah.
of course, bulk scaling dimensions are not affected by the boundary, by the details of boundary conditions. However, boundary scaling dimensions. So here, O hat here is an operator sitting on the boundary or in the vicinity of the boundary. And I take the limit when there are these two operators sitting near the boundary, and I take their separation to be very large. So this is how this scaling.
Yeah, no, I understand this, but I can imagine that, for example, kind of boundary conditions are fixed, right? That in this way, it's not like, you see, because it implies that there is some kind of freedom, some degrees of freedom which are living on the boundary, right? Because when you are talking about this, so if, I don't know, in kind of extreme case, if my boundary condition are kind of completely fixed, so I have particular distribution at the boundary, then there is no any kind of degrees of freedom there, right?
No, Arkady. In that case, it's still you can still talk about these boundary operators. The way you can think about them is take a bulk operator that's not exactly on the boundary, but close to the boundary. So two bulk operators whose separation along the boundary is much bigger than the distance to the boundary. Then these bulk operators you can think of as boundary operators, and this dimension delta hat for them will in general be different from.
I see. So in this way, it would be in some way, whatever boundary condition I put would be nearby would be another boundary, right, where this your degrees of freedom would be living. I mean, in the vicinity of.
You can think of it that way. Yeah.
Okay. Thank you.
But in general, there will be some discrete number of boundary universality classes.
Okay, thank you.
Yeah, where close. Yeah. So why revisit this problem, this old problem? There are several reasons that this problem has received some renewed attention in the last few years. First reason is just improved understanding of conformal field theories, in part due to the advances in the Bootstrap program. The second reason comes from the physics of topological phases, in particular symmetry-protected topological phases. So we know that SPT phases are gapped in the bulk, and they have protected edge states. Now you can ask, suppose the gap of the SPT closes. So suppose you, say, drive the SPT to a critical point. At the point where the bulk closes, does anything of the boundary survive? Does anything of the protected boundary mode survive? And it was realized that in some cases the answer to this question is yes. Sometimes something of this boundary mode survives, and this goes under the heading of gapless SPT. So I believe one of the first examples of this was discussed by Tarun Grover and Ashwin Vishwanath some time ago, but actually there have been many examples constructed in recent years. So this is another reason why boundary criticality has become popular again, right? This is an example of boundary criticality. You have SPT driven to a critical point, so a gapless system in the bulk, and you're studying some kind of boundary for it. So I'll come back to this problem later in my talk, but actually most of my talk is just going to be about classical statistical mechanics, and I'd like to convince you that even there some very basic questions have not been settled or even asked in the literature. All right. So the model that I'll be mostly talking about is perhaps the simplest model in statistical mechanics, the classical ON model in d dimensions. So let me remind you about the definition of this model. So first of all, we have a hypercubic lattice in d dimensions. D is always the bulk dimension here. And we have classical spins sitting on the sides of this lattice. So classical spins are just n-component vectors of length 1 that are free to fluctuate. And we have nearest neighbor coupling between these spins, like this. And if you study the system in the presence of a boundary, we allow the coupling on the boundary k1 to be different from the coupling in the bulk k. So we have a dimensionless parameter kappa, which is a ratio of these two couplings. And in addition, of course, we have temperature. So this is a classical model. So we'd like to study the phase diagram of this model in this. Oh, I see someone is pointing out the references. Thanks. Yeah, and we have the phase diagram of this model in this two-dimensional plane that we'd like to understand. And if the dimension of the system, if the bulk dimension d is greater than 3, by the way, this little d will always refer to the bulk dimension, this is believed to be the phase diagram. This is the accepted phase diagram. So let's point out some features of this phase diagram. First of all, of course, there is a bulk phase transition at t equal to tc, where the bulk goes from paramagnetic to ferromagnetic. Now, what happens to the boundary at this bulk transition? Well, as long as the surface coupling K1 is not too large, the boundary orders at the same temperature as the bulk does, right? So, this boundary universality class is known as the ordinary boundary universality class. However, if you make the surface coupling large enough, then the surface can order at a temperature which is higher than the bulk Tc, right? So then what happens as you're lowering the temperature, first, both the bulk and then surface becomes ordered. The bulk is still disordered in this region here, and the green transition is a purely surface transition, so purely d-1 dimensional transition in the ON Wilson-Fisher universality class. Nothing very interesting about it. And then, as you keep lowering the temperature, at some point you cross the bulk ordering transition, right? So here the bulk orders in the presence of a boundary which is already ordered. This is known as the extraordinary universality class, and we will come back to it in a second. And finally, there is this special transition, which is a multi-critical point, separating the ordinary and the extraordinary. So ordinary, special, and extraordinary are three boundary universality classes as long as the bulk dimension d is greater than 3. June?
Yes, naive question. So I also just encourage people to ask. In your phase diagram, when you start from higher temperature, lowering down temperature to low T, you have the surface order first, right? Generically, surface order first, or surface and bulk order together.
In this region, right. Yeah.
And in the other region, they order together in
yes.
some critical line. But whether it's possible to have just naively ask, whether it's possible to have a bulk order prior to surface order, the other way around. Is it possible? Is it some?
Not really, because as long as there is coupling between the surface and the bulk, then if the bulk orders, the surface also orders. So this is why this line, which you could naively kind of draw as going if you were just kind of drawing the phase diagram of the surface layer, you would say, oh, maybe it goes down here. But if the bulk is ordered, the surface must also be ordered. So that's why. Yeah, good question.
In your example, you mentioned this paramagnet and ferromagnet on two sides of the phase diagram. So those are, let me just make sure. So one is gapped, the other is gapless.
It depends on the on n, whether
right.
n is bigger than 1 or equal to 1. So if n is well bigger than 1, then the ferromagnet has some goldstone,
right.
some goldstone modes.
Okay.
Yeah. Here, really, I'm talking about a classical
right.
classical model. So really, you should not be talking about gapless, but about finite correlation length versus versus power law correlation functions.
Mm-hmm. But if I want to change the classical dynamic model to quantum system, I should go interpret in the sense of one-dimensional lower in the space.
That's right.
Yeah. Would you also comment that maybe later at some point?
Yeah, actually, I will discuss very concrete quantum lattice model that maps to the same classical universality class, at least in the bulk.
Right. Thank you.
Yeah. So so this is the phase diagram if the bulk dimension d is greater than 3, and if there is no symmetry breaking field either on the surface or in the bulk. Now you can also add a symmetry breaking field to the surface, and in that case, it's believed that there is just one universality class, the so-called normal universality class. Right? So this normal universality class, in the presence of a symmetry breaking field, is believed to be realized for all values of the surface coupling K1. And the interesting point here is that actually, if dimension is bigger than 3, it's believed that the normal universality class is essentially the same as the extraordinary universality class. That is, it doesn't matter whether your symmetry on the boundary is broken explicitly by a symmetry breaking field or spontaneously by a surface or the parameter, the transition is essentially the same. And this is almost obvious for the case of Ising spins, n equal to 1, but it's also believed to be true for the case of continuous spins. Associated with the surface decouple here at this extraordinary transition, and it's in the same universality class as the normal transition.
Max, but returning a little bit back to my original question, I wonder that in this way, how to say, there should be kind of scale associated with the boundary where, this phenomenon you mentioned that, when you're approaching the boundary, you have this stuff. So it should be a physical scale, right? So in certain sense, it's like a size of the boundary in this dimension, right?
Very good question. So we can ask about in general. Say you take we look at 2-point function. There is one. And both points are in the bulk, and you can ask what is the scaling form. So clearly, so everything is conformal, right? So in principle, you would say, oh, well, there is the separation along the boundary, and then there is the distance to the boundary. So there are in principle 3 variables: z, z prime, and rho, the distance along the boundary. So you would say, oh, it's a 2-point function is a universal function of 2 variables, rho over z and rho over z prime, or other way around. But actually conformal, so this is just from scale invariance. Conformal invariance makes it a function of just one variable, which is some combination of these two ratios, z over rho and z prime over rho. So in one limit, that function goes kind of to the boundary limit, and in the other limit it kind of goes to the bulk limit. So you have 2 points, right? 2 operators at 2 points, and you can either kind of fuse them, bring them close together. This is kind of the bulk limit, or you can separate them very far along the boundary, and this is essentially the boundary limit. So this.
But there is no in this way this scale, the distance to the boundary would enter inside of this ratio.
That's right. That's right. That's right.
I see.
Yeah. In principle, there is always some kind of finite correlation length, as you know, finite or crossover length associated with the boundary. But yeah, this is kind of non-universal physics that we are not interested in.
Okay. Thank you. Sorry to interrupt you with this, but.
No. This is a very good question, actually. Right. I saw there was also a question in the chat, which was whether this is a spinful Hamiltonian. So this Hamiltonian actually has only classical spin degrees of freedom. So there are no charge degrees of freedom. So first of all, this is classical. So yeah, you should think of electrons, if you wish, as you know, pinned to sit on each lattice side, and the only degree of freedom left is spin, and more than that, we are treating this spin as classical. All right. So let me proceed then. Yeah. So the main question I'd like to ask in this talk is what happens to this phase diagram when the bulk dimension d is equal to 3, right? So this is quite reasonable question. After all, we live in 3 dimensions. Right. So first of all, if we are dealing with Ising spins n equal to 1, then the story is exactly the same. Same topology of the phase diagram, same universality classes. But the physics becomes more interesting for the case of xy spins, so n equal to 2, O2 model. Right? So if bulk dimension d is equal to 3, then surface dimension is equal to 2. Right? In 2 dimensions, we know that with xy spins, we cannot have true long-range order. We can only have a quasi-long-range order, strictly in 2 dimensions. So when we go to a region with large surface coupling and start lowering the temperature, we enter here a phase not with true long-range order, but with quasi-long-range order. So 2-point function of the spins on the boundary falls off as a power law, and then this surface transition is a Kosterlitz-Thouless transition. Okay, so that's well understood. However, the question I'd like to ask is, well, what happens here at this extraordinary transition? So when the bulk out of this surface phase with quasi long range order, and this question has not really been addressed in the literature. The only discussion of it that I could find was in this old numerical paper that did classical Monte-Carlo. And they discuss several scenarios for what might be happening at this extraordinary transition in this case. But one of the scenarios was the following: that actually, even though above the bulk TC the surface cannot have true long-range order, maybe directly at the bulk TC the surface has long-range order. That is, there is a jump in the surface order parameter across the bulk TC, and this seem to be roughly consistent with their Monte-Carlo simulations. This is kind of a strange scenario, but it's actually quite hard to shoot down immediately. And the reason is that while above the bulk TC we have a finite correlation length in the bulk, so essentially we can integrate the bulk out and get an effectively local boundary Hamiltonian. If we try to do the same at the bulk critical point, then we end up with effective boundary Hamiltonian with power law coupling between spins. And we know that when we have power law coupling between spins, in principle, Mermin-Wagner theorem does not apply anymore, and we could have a true long-range order. But it turns out this does not actually happen. So I'll show analytically that this is not what happens. Instead, what happens is that at this extraordinary line, for xy spins, the 2-point function of spins on the boundary behaves in the following way. it falls off as a power of logarithm of separation of the two spins, with the power being universal, q being universal. So there is no true long-range order, right? The two-point function goes to 0 at large separation, but it goes to 0 extremely slowly. Another property of this extraordinary transition is that if you approach it from this region here with quasi-long-range order, as we already said, the two-point function of the spins on the boundary falls off in a power law manner, and it's a variable exponent. But this Lagrangian parameter kappa diverges logarithmically as we approach the extraordinary line, right? So this power in the power law actually goes to 0 as you approach the extraordinary line. So I term this the extraordinary log universality class to distinguish.
Sorry, I have a question, if I may. So actually two questions. What sets the scale in the log? So it's log x over something.
Non-universal physics. If you wish, K1.
So the correlation function is not universal.
There is some non-universal part to this. As you're saying, whenever you have log x, you have to divide by something.
Well, right, and usually the something can be absorbed in something else, like in redefinition of the operator. But here you cannot do that.
That's it's not really a conformal point. So there is one coupling that's marginally irrelevant, and if you wish, you can absorb the non-universality into that irrelevant.
So the theory is not conformal. So
That's
there's
right.
probably some effective description of it with some dimensionful parameters in the bulk or the boundary.
There is one coupling on the boundary which is marginally irrelevant, and essentially all the non-universal physics can be absorbed into that coupling.
So it is universal. It's the coefficient of this marginally irrelevant operator.
That's right.
Okay. The second question I have is about the second bullet. Is this on the boundary or in the bulk? I missed what you said.
This is still so both of these are boundary correlation function of the order parameter, but this one is slightly boundary, right? So as you are approaching the
x that appears here, is it x that appears here? Is it a coordinate along the boundary?
That's right.
So these are two operators at the boundary, and then when is it a power and when is it 1 over log?
So if you go to t greater than tc, right? So you go away, you perturb in the bulk by the marginal, by the relevant operator to kind of go to the bulk paramagnetic phase. Then on the boundary in this regime, you will have at long enough distance scales, you will have this power law behavior, right? So essentially, if I'm not mistaken, on distances smaller than the bulk correlation length, you have this behavior. On distances larger than the bulk correlation length, you have this behavior.
And is this some kind of a conformal field theory, an effective conformal field theory at large x or not?
It is just a Lagrangian liquid, right? So you're sitting here, right? You're sitting in this phase. So the bulk at long enough distances is now completely gapped. There is a finite correlation length. So there is only a surface, and this surface is just described by the compact boson. And if you wish, this kappa is the radius of this compact boson, or inverse radius. I forget the nomenclature.
Well, it depends on whether it's 1 over 2 over parentheses 2k or 1 over 2 close parentheses dot k.
K is in the denominator.
Then it's r squared.
Okay, so k is r.
R square, not R. But that's okay, doesn't matter.
Can I maybe also, because you're interrupted all the time, so maybe I'll have to disruption. So just to carry on this question that Nathan had. So basically what I was saying is that when you're approaching the extraordinary line, the thickness of the boundary layer sort of grows and interaction between spin grows. So indeed it's Lagrangian or an Apostolus rather. And basically it's capital K is effective interaction constant between surface spins. So system becomes, I guess, more and more rigid.
Yeah, the surface how it's called spin stiffness.
Yes, this goes up because your surface layer becomes thicker and thicker.
I don't know if I would think of it as thicker and thicker, but it's correct that the surface stiffness becomes larger and larger.
Well, it is because you have psi bulk and K depends on the psi bulk, so that's definitely what happens. But the other question is that suppose I go away from surface. So I understand the surface is special, but if I go into the bulk, far from the surface, and just follow the line from ordinary to extraordinary, what happens to correlation function? So I know what happens, what is correlation function at the blue line, okay, that's known. So when you cross into extraordinary, what happens to correlation function?
Sorry, you want to sit exactly at bulk TC or?
Yes. No, I want to sit, I want to sit exactly at the line.
You want to sit along this line and
basically TC is not universal. I mean, I don't know what TC is, but I want to sit on the line.
On the transition line.
Yeah.
Okay. Yeah. And you want to understand what happens as you tune.
I want to understand what happens with the correlation function when you go from blue to brown, far away from the boundary.
Well, if you're really far away from the boundary, then you don't care what's happening on the boundary, right? You just bulk correlation function. It's all the same. But if you're interested in the so there is some scaling function, right? For each one of these three classes, there is some scaling function describing the 2-point function in the bulk. As I already told Arkady, it's a scaling function of just one variable. That's a combination of the distances to the boundary of the 2 points and the separation.
Yeah, I hear what you're saying, but it's not the answer nevertheless. So once again, so I take this this function as a function of the distance in the plane, but this plane is far away from the surface. So I mean, if I'm blue line, then it's a parallel function. I know it, and I know the exponent. Do you agree?
If you're really in the bulk, I don't
know what it means really. I mean, the word really should be qualified somehow.
If you're in the bulk limit, then there is just one exponent, which is the bulk exponent, and it's known to ridiculous accuracy, but it has nothing to do with boundary physics. If you're if you're interested in the boundary exponent, then it's different in the ordinary, special, and extraordinary classes. In fact, for the extraordinary classes, it's not an exponent; it's this log. Is this log form. Now,
so basically everything they're telling is about you fix the distance to the boundary, whatever you pick for the distance, but you don't vary the distance to the boundary. It may be 0 or maybe 1 centimeter, but it's not a variable for you.
Well, we can do either. Which limit are you interested in?
Well, then I would be interested probably if I look at some point at the brown line, fix x equals 0, and then separate points in z direction.
And
I can keep both these large, but the difference between these is a quantity that I'm interested in.
So you kind of want. Let me go back to the picture here. So you want 2 points,
yeah,
kind of vertically above each other.
Right.
And
so there is Z1, Z2. Okay, so let's use difference and sum instead. Okay, and suppose the sum is larger than difference, much larger than difference.
mm-hmm.
Okay, so what is the function of the difference at fixed sum?
What is the function? Just a second. Yeah, if I'm not if I'm not mistaken, if they're really on top of each other, then this is the same as the bulk correlation function. So nothing.
Okay. Yeah, that's what I wanted to know.
Yeah.
Thanks. Yeah, and again, sorry for interrupting.
No problem.
I don't know, it might be too much of asking, but still, when you are showing the two boundary, regimes, right? One which one power of logs and another power of x. I wonder about possibility that you can take a limit where k is, I don't know, large or whatever. So it should be kind of, way of transition between these two regimes.
You want to understand the crossover from.
Yeah.
So this is kind of sitting here, right? And then as you make x larger, you first go from this regime to this regime. So you want to understand the entire crossover. This is of course more difficult problem. I'm thinking whether we can actually. Yeah,
No, because it looks like a possibility, like say k goes to infinity, then it's like becoming like log in a sense, right? When you have x in small power.
Yeah, it at the very least it requires it requires more data. So at the very least, so first of all, you need to kind of know something about the off-critical theory, right? Because this behavior, it's really in the off-critical.
I see.
So you need to know some correlation functions in the off-critical theory, which we don't actually know precisely.
But I'm not even sure that it's universal, because why it should be universal? Because still this log, as somebody said, has a denominator which is a microscopic length. So it's not obvious that these two functions, that the crossover is universal, is it?
Well, as we were discussing with Nati, the non-universality can be in principle can be absorbed into one parameter, which is flowing to zero logarithmically as a function of system size.
Yeah, that's right. Yeah. Okay. Thanks.
Mm-hmm. Okay, let's see how we are doing for time. All right. So let's yeah. So this
don't worry about time. There's no time constraint.
This is about this xy universality class, and I'll substantiate these claims with some RG analysis. Maybe when I come to the RG analysis, maybe some of these issues will become more clear. Yeah, but first I also want to discuss what happens when n is greater than 2, right? So say we have Heisenberg spins, say we have n equal 3. So in this case, if t is above the bulk Tc, then we have a finite correlation length in the bulk, and therefore the boundary must also have a finite correlation length. We know that for n greater than 2 in 2 dimensions, that is the surface dimension, we cannot have either long-range order or quasi-long-range order. We must have a finite correlation length. So therefore, in principle, there is no need for a separate extraordinary transition in this case. It's possible that the phase diagram is just like this. There is just the ordinary universality class for all values of surface coupling K1. However, it's also not ruled out that that at Tc, part of the boundary is in the ordinary universality class, and part is in some other universality class, which I'll call extraordinary for the lack of a better name. So which one of these two is realized? Turns out that the answer depends on n, on the value of n. For large but finite n, we indeed have this picture on the left here with just the ordinary universality class for all values of the surface coupling. On the other hand, for n just above 2, we know for certain that we have a phase diagram here on the right with a separate extraordinary portion of the boundary, and here the spin-spin correlation function again decays as a power of logarithm. Now this power depends on n. So this is the result of the RG analysis that I will describe shortly. But first, let me kind of give some intuitive arguments in favor of these two regimes. So first of all, let's begin with this regime when n is large. Let's first go to n equal to infinity. So for n equal infinity, I can do large n calculations in any dimensions. And in dimension d equal to 3 at n equal infinity, I find no special fixed point. This is kind of a known result in the literature. One only finds an ordinary fixed point. So this is perhaps consistent with the phase diagram like this. You can also look what happens if you make bulk dimensions slightly larger than 3. So if bulk dimension is larger than 3, then we know that we have this phase diagram here. And in particular, we can describe all these 3 universality classes in the large n expansion. In particular, I can sit at the special transition here and do 1 over n calculations. And here is what I get for the scaling dimension of the boundary or the parameter at the special transition at large n, and for dimension d close to 3, just slightly above 3. So the 1 over n squared term is not known, but the order 1 and order 1 over n terms are known from the work of Ono and Akabe in the 80s, and both of these terms are proportional to epsilon when you set d equal to 3 plus epsilon.
But it is true also for negative epsilon?
No, this is for negative epsilon, one does not find a special fixed point, but for positive epsilon, this is what you get. Mm. So what is this suggesting? Well, it's suggesting that as epsilon goes to 0, the scaling dimension of the surface or the parameter goes at the special goes to 0, it means that the operator condenses. Now we know that the extraordinary fixed point is one where the boundary spin condenses. So what it looks like is that as d is approaching 3, and if n is large, the special fixed point is approaching the extraordinary fixed point, and when d is equal to 3, they just collide and annihilate. And we have the picture here with only the ordinary fixed point left. And indeed, this picture is confirmed by the RG analysis that I'll present shortly. So we understand this limit of large n now, or at least we have a guess. What about n just slightly larger than 2, the opposite limit? Well, we know that when n is equal to 2, we must have these 3 universality classes: ordinary, special, and extraordinary. And now, as we just discussed, fixed points do not just appear and disappear by themselves as you change some parameter. They appear and disappear in pairs. But all these 3 fixed points are far away from each other. So if you make n just slightly larger than 2, you cannot immediately lose these fixed points, so they must survive. So for n just above 2, we must have a phase diagram like this. Okay. So let's now discuss renormalization group analysis that supports these pictures. So let me begin with the following. Let me imagine that I take my I take my surface layer and I turn off the couplings of the surface layer to the bulk. And so I just have a two-dimensional surface system, and I want to study actually the regime when the surface coupling K1 is large, right? So where we are kind of in the would-be extraordinary regime. We want to understand this part of the phase diagram. Okay, so if we turned off the couplings of the surface to the bulk, then you can just describe the surface by a nonlinear sigma model for the surface order parameter. I call it n here, and here it is. And we want to understand this nonlinear sigma model in the regime of small coupling G. Well, of course, Polyakov taught us about this theory. We know that G runs in the following manner, and in fact, G runs to infinity in the infrared, which signals the fact that this nonlinear sigma model for n greater than 2 in 2 dimensions has a finite correlation length. So no, nothing new there. The question I'd like to ask: what happens when we now turn back on the coupling of the surface to the bulk? And let me first just tell you the answer. Maybe if I have time at the end of my talk, I'll describe the calculations that lead to this answer. But the answer is the following. The only thing that happens is that the coefficient of the G squared term in this beta function is modified. So it's same kind of flow, but instead of the coefficient n minus 2, we now have a coefficient alpha that has two contributions. One contribution is this pure surface contribution that Polyakov has taught us about, and the second contribution is a contribution from the bulk. S here is a universal number, and it's related to the ratio of certain universal amplitudes at the normal fixed point. Remember, normal fixed point is one where you turn on a symmetry breaking field on the surface. So if we have time, we'll discuss that in more detail. For now, let's just remember that S is a universal number.
But it looks a little bit like, kind of going to effective n, right? To some, no, at least kind of superficially.
You might
see, because I can say that influence of the bulk is kind of changing your. No, I wonder. It's not just about rewriting as effective n, but about indeed counting degrees of freedom, right? In certain sense.
That's interesting. Yeah, I haven't thought of it this way, but of course symmetry is different for different ends, so it's not clear to me.
Mm-hmm. And the point is that nothing depends on kappa on K1 over K2.
S depends on n. The S is a universal number that depends on n. Kappa only goes into the initial value of G.
I see.
So, G at lattice scale. So what is the fate of this theory? Well, the answer depends on whether alpha is positive or negative. If alpha is positive, then in the infrared, G flows to 0 logarithmically, and this is the advertised extraordinary log fixed point. G is this marginally irrelevant coupling, which we already alluded to several times in discussions. At this fixed point, we can integrate the RG equation for n, the Cullen semantic equation, if you wish, and this is the behavior of the two-point function of n that we obtain. Indeed, it decays as logarithm of separation to a power q, and this power is related precisely to alpha. Okay, so this is the advertised extraordinary log fixed point. On the other hand, if alpha is negative, then the G equals 0 fixed point is unstable in the infrared. Where does the theory flow? We will discuss shortly. Now, is alpha positive or negative? Well, that depends on the value of n. In general, I cannot calculate alpha, but I can calculate at least its sign in two limits. First of all, when n is equal to 2, then the boundary contribution to alpha vanishes. We only have the bulk contribution. This bulk contribution is manifestly positive. So we know that when n is equal to 2, alpha is positive, so we have the extraordinary log physics at n equal to 2. On the other hand, when n goes to infinity, we can use large N to calculate this universal number S, and this is actually the value that one gets, we see that it's negative. So alpha has to change sign as we increase n from 2 to infinity, and I will assume in my talk that it changes sign just once at n equal to nc. For n smaller than nc, we have a stable extraordinary log phase in the infrared. For n greater than nc, we don't know yet what happens. We will discuss in a second. What is the value of nc? I think the honest answer is that we don't know. If you just naively extrapolate from large n, then we would say nc is equal to roughly 4. But I think the honest answer is we don't know. All right. So what is the evolution of the system across this nc? Well, really, when n is equal to nc, the leading term in the beta function vanishes, and the physics is controlled by the subleading term g cubed. So so physics really will depend on whether the coefficient of this g cubed term is positive or negative. Let's discuss both cases. Right now we don't know what the coefficient is from analytical considerations, so we better discuss both scenarios. If b is positive, then just below n equal to nc, we find an infrared unstable but perturbatively accessible Rg fixed point at some small value of g. We can calculate all the scaling dimensions at this fixed point, and we identify this fixed point with a special fixed point, right? We know that when n is equal to 2, we have a special transition between the extraordinary regime and the ordinary regime. So in this scenario, this special fixed point just approaches weak coupling as n goes to nc. At n equal nc, it collides with the extraordinary g equals 0 fixed point, and they annihilate. And for n greater than nc, we only have the ordinary fixed point left. So this is perhaps the simplest scenario for the evolution with n. However, if b is less than 0, we have a different physics. Just above n equal to nc, we have a infrared stable, perturbatively accessible fixed point, and essentially what happens is that the extraordinary log fixed point moves off away from g equals 0 to some finite value of g, but this is still an infrared stable fixed point. But now it's really a true boundary conformal field theory. So now the correlation function of the order parameter in this extraordinary regime is truly power law. Since we know that at n equal infinity we only have the ordinary fixed point, then this extraordinary, what we call extraordinary power fixed point, must eventually somehow disappear, and the simplest scenario is that it collides with the special fixed point at some yet larger value of n. So this is the second scenario. It's a little bit more exotic than the first scenario, but based just on analytics, so far we have to consider. So really, this is about all all the analytical conclusions we can draw at this point. So here is the phase diagram in the two scenarios. Here is the first scenario, and here is the second scenario, again as a function of n and kappa. So the remaining questions is which of these two scenarios is realized, and what is the value of nc? In particular, whether nc is greater than 3, right? Because 3 is the kind of the smallest integer value of n, for which we don't really know the phase diagram. So let's see how we are doing for time. But in the next section of the talk, I'll discuss what is known from numerics about these questions. But first, any questions at this point? All right. If not, let me go on. So before my paper appeared, there were actually only two.
I actually have a question. So imagine I just started from a three-dimensional. I'm thinking about it as kind of as a Lagrangian in Euclidean Lagrangian field theory. It's the same thing. So I can formulate this problem in the continuum. So I have a Lagrangian, and Lagrangian doesn't have too many parameters, and it should describe all these phase transitions.
Yeah.
Why can't you just do it analytically in this framework?
You can, it's just you might not be able to solve the theory. So later we can discuss a pretty nice description of the. It's not difficult to formulate a UV.
There's a UV continuum Lagrangian that describes your system.
That's right. Yeah. So here is, for instance, a UV continuum Lagrangian. You take this.
Phi is the standard Wilson-Fisher for SON.
Phi is a standard Wilson-Fisher for SON. You can choose some boundary condition that you like. Maybe choose Dirichlet, such that this S ordinary describes the ordinary fixed point for the boundary.
Why don't you just say that phi equals n on the boundary?
You can also try to do that.
They're both SON vectors, so you can have a boundary condition that, I guess this is S tilde of yours goes to infinity or minus infinity.
You can also do that. I'm not sure it will somehow simplify life, but
well, there are fewer fields. But then you just work in perturbation theory. There's a small number of coupling constants, so you can just work out in perturbation theory and see what happens.
The problem is that S tilde is relevant.
Well, let's set S tilde to infinity.
Okay.
I'm too lazy to compute whether it's plus infinity or minus infinity. The one that sets phi equals n.
Okay.
Right. This is the picture that you had, right? At every point in your three-dimensional box, you have phi, and it just that it has slightly different interactions on the boundary. Right, so if S tilde goes to infinity, it wants n hat n dot phi to be a 1, which means that phi equals n. So you have one field phi and some simple interactions.
But you assume that G is fixed in this procedure?
No, it's another coupling constant. So there's one coupling constant on the boundary G, and there's some coupling constant in the Wilson-Fisher theory, and we can just start computing.
I think you will run into trouble, because this kind of Dirichlet boundary, if you impose Dirichlet boundary condition, then this phi actually in some sense goes to 0 on the boundary. Okay, you can say let me get, instead of Dirichlet, I just impose this phi equal n, but that's somehow like a free boundary condition, which again is not quite what you want to.
But that's what you said. Isn't that what you said before? You have spins, and the spins are, you didn't give them different names on the boundary and in the bulk. And you just said that the spins have slightly different k's inside and on the boundary. So it seems to me like what you have is exactly what this thing describes.
Yeah, somehow, yeah, I think it will be quite tricky. So the reason maybe is the following. So this phi to the fourth field theory, right? We control well in the limit when the dimension is close to 4. Right? In that limit, we know the phase diagram. We know there is ordinary, there is special, and there is extraordinary. We can describe each one using 4 minus epsilon expansion precisely in the same way, Nati, as you're describing. Really, the question is, what happens to this extraordinary class?
I understand that once the system becomes strongly coupled, it's hard to compute, but I'm just curious what perturbation theory would tell you. If I start in the UV from this system, I can at least in the UV see what happens to the various couplings.
I think the
I
problem.
don't want to derail you, so I withdraw the question.
Yeah, let me. I think the reason it's tricky is that you're trying. We know what this extraordinary phase is in mean field. We want to understand beyond mean field, and that's the tricky part.
Okay.
But I think maybe if I have time, I'll talk about the RG analysis slightly later. Maybe it will make more sense then.
Okay.
Yeah, but first let me talk about numerics. So here is, before my paper came out, there were actually only 2 numerical studies of the case n equal to 3 in this regime of large boundary coupling. And the first one of them was actually inconclusive. So for small boundary coupling, they saw that this system flows to the ordinary universality class. But for large boundary coupling, they could not actually track the true infrared fate of the theory. The slightly subsequent study by these authors claimed or pointed out the possibility that for n equal to 3, there is a special transition on the boundary. And the way they saw this, they looked at the analog boundary analog of the Binder ratio, and they saw that there is a crossing as a function of kappa of curves with different system sizes. So different curves here correspond to different system size, and such crossing indeed happens when you have a fixed point. So putatively there is a special transition here at this value of kappa, but they were not able to describe actually what happens on the large kappa side of that transition. What is kind of the extraordinary phase. Here's actually a study for n equal to 4. Again, there is a crossing point. Yeah, looks actually quite similar to n equal to 3. So after my paper came out, there was a study by large-scale Monte-Carlo simulation. Again, he looked at the surface Binder ratio. Again, he observed what seems like a crossing point as a function of the surface coupling and for different system sizes, which he identifies with a special transition. So his claim is that there is a special transition for n equal to 3. And here are the exponents he extracts at that transition. So here is the scaling dimension of the boundary or the parameter, and here is the inverse correlation length exponent. Keep these numbers in mind. Furthermore, Francesca has explored one point in the putative extraordinary phase for n equal to 3, and his findings are roughly consistent with extraordinary log behavior. So here is the 2-point function on the boundary in this extraordinary regime. You see, horizontal axis is log scale, so this correlation function falls off very slowly, and it's roughly consistent with the power of logarithm, like this. Perhaps even better signature is to look at the stiffness of the system. And remember, we are saying that in the extraordinary log phase, the surface stiffness grows logarithmically. And in fact, the surface stiffness will dominate the stiffness of the entire system at large system size. And indeed, we see that the stiffness grows roughly logarithmically, like so.
So wasn't it for n equals 2, or it was more general than? I realize that n equals 2 is indeed you have this log, but you're saying now that even if n is not
remember,
2.
The conclusion was that there exists an NC.
Yeah, okay. Sorry, yeah, I got it. Yes, yeah.
And really the question is whether 3 is smaller than NC
Right,
or 3 is bigger than NC. And
right. So yeah, so
yeah,
n less than NC is essentially 2. Yeah, okay.
yeah. NC cannot be strictly 2, but
Right.
here it actually is looking like NC is greater than 3 because we have this logarithmic behavior.
Right.
There is no saturation, and I think the largest point here was something like 400 lattice spacing. So this is quite convincing to me. Right, and Francesca extracts this alpha, and it's something in this range. You can actually extract alpha both from the stiffness and from Q, and they're kind of the same order of magnitude. So this is kind of the best classical Monte-Carlo data for n equal to 3. There was also so it looks like n equal 3 is below NC, but we don't know. There is an extraordinary log phase. There is a special transition. We don't know yet whether we have scenario 1 on the left or scenario 2 on the right. There was also a study of the n equal 2 problem after my paper came out, and here again things seem to be consistent with the extraordinary log universality class for large surface coupling. So again, this is the 2-point function of spins on the surface. Seems to be consistent with the power of logarithm. Here's the stiffness, seems to be consistent with logarithmic growth. The slope seems to be roughly the same at various points in the extraordinary phase. So all of this looks good. And in fact, this exponent q in the 2-point function, remember analytically is related to alpha in this way, and extracting q from here and alpha from here, this formula seems to be verified, and alpha for n equal 2 is something like 0.27. So I think there is pretty strong evidence for n equal to 2 that the extraordinary log phase is there. Now remember, in our analytical considerations, alpha had to change sign as n increases. So alpha has to decrease as n increases, and indeed this is what's numerically seen. Alpha decreases from n equal 2 to n equal to 3. So everything so far is consistent with the analytics. Now, which one of these two scenarios is realized? Is it the one left or the one right? Well, I think there is probably not enough numerics to kind of answer this question without doubt. But if I had to put my money, I would put it on the scenario on the left here, because in this scenario, remember, as n approaches NC, the special transition occurs in the perturbatively accessible regime, and in particular, these two exponents should become small as n approaches NC. Well, here is the data on these two exponents at the special transition as a function of n, and indeed it looks like they're becoming small as n increases. I don't know whether we should really trust this data for n equal to 4, but yeah, your call. But at least if I had to make a choice, I would say I would put my money on this simpler scenario here. Okay, so this is all the classical Monte-Carlo that's available at this point. It would be nice to have a more careful examination of the n equal 4 theory in classical Monte-Carlo. So far that has not been done. There is also a lot of quantum Monte-Carlo actually on related models. Let me see how I'm doing for time. Yeah, let me talk about this quantum Monte-Carlo. So
don't worry about time. Just say everything you prepared.
Yeah. Okay, I just don't want to exhaust the audience.
as long as he can finish before midnight, I think it's okay.
I can certainly. I hope I can certainly finish before midnight. All right. So
you can say that there is no boundary in time for you.
very good. Yeah. So so here's a class of quantum models I'd like to discuss. It's quantum spin models in 2 dimensions. And actually, different lattices have been considered, but for simplicity, let's consider a rectangular lattice and quantum spin model with antiferromagnetic nearest neighbor couplings, but couplings which are staggered like this. So coupling on the black bonds is weaker than the coupling on the red bonds. So this model has been studied in the bulk a long time ago. So what are kind of the limits of the phase diagram? When this coupling on the red bonds is much stronger than the coupling on the black bonds, then the spins on the red bonds just lock into singlets, and we have a paramagnet. On the other hand, when JD is equal to J, we have a square lattice antiferromagnet that realizes the nail phase. So there has to be a phase transition as a function of this parameter, and in fact, numerical simulations have verified that this phase transition, this bulk phase transition, is continuous and is in the classical 3D or 3 universality class. So nothing exotic about that. The same universality class we've been talking about all along, but yeah, with n equal to 3. The recent developments relate to the boundary criticality in these kinds of models, actually, there are 2 kinds of boundaries one can study in this model, so-called non-dangling boundary and dangling boundary. So the non-dangling boundary, the boundary spins terminate on the strong bonds, and the dangling boundary, the boundary spins terminate on the weak bonds. And when we go to the bulk critical point and study the boundary physics on these 2 edges, we find very different physics. Rather, well, I should really say Stefan Wessel and his collaborators find very different physics. For the non-dangling edge, they see a boundary spin scaling dimension, which is quite close to one seen in classical O3 model at the ordinary fixed point. However, at the dangling edge, a very different scaling dimension of the spin is seen, one which is much smaller, something like 1/4. So what's going on? Well, remember actually this quantum Monte-Carlo studies were done back in the day when people thought that for n equal to 3, you have only the ordinary universality class. Actually, kind of the picture that is implicitly there in the literature is that for n equal to 3 in classical models, you only have the ordinary universality class. So this was really surprising. This was really surprising, and what people said, oh, it has to do with quantum physics. In particular, the initial models that people studied were spin 1/2 models, and for spin 1/2 model, already in the paramagnetic phase here, you have something interesting going on the boundary, right? So the spins on the red bonds are locked into singlets, but you have dangling spin 1/2s along this edge, and we know that spin 1/2 chain in 1D is gapless, just Heisenberg chain in 1D described by SU2 level 1 conformal field theory. So you already have a gapless edge here in the paramagnetic phase. So clearly the boundary universality of this dangling edge for spin 1/2 has to cannot be ordinary, because for ordinary universality class, once you go into the paramagnetic phase, you have a trivial boundary, not a gapless boundary. And in fact, you can think of this problem as a kind of transition out of a weak SPT, right? You can think of this paramagnetic phase for spin 1/2 spins as a weak SPT protected by translational symmetry along the edge and spin rotation symmetry, right? You can think of each one of these vertical chains as a Haldanean chain with a dangling spin 1/2 at the edge, right? So this paramagnet is a weak SPT, and we are exactly in the scenario I discussed in the introduction, where you have a SPT, you tune this SPT to a critical point, and you ask whether anything remains of the protected edge of the SPT. So this is what people thought has leads to this difference between the dangling edge and the non-dangling edge. The real surprise came when people repeated the same study, but for s equal 1, for spin 1. And they saw, again, very similar physics on the dangling edge with a boundary exponent of the nail or the parameter, essentially the same as for s equal 1/2. And this was really surprising, because for s equal 1, we know that Haldane chain is gapped, so there is no, this phase here is not a SPT, is kind of a trivial paramagnet. So what's going on? So I think the honest answer is we still don't know. One possibility that has been raised is that this dangling edge in all of these models, and there are actually a lot of models that have been studied with different geometries and with s equal 1/2 and s equal to 1, one guess is that perhaps it's controlled by the special transition, right? So we know that in the classical O3 model, we have, at least now, we seem to, this seems to have been established by Francesca Tolden numerically, that n equal 3 is below nc. We have the special transition, and these are the exponents in the classical O3 model at the special transition. And notice in particular this delta n, roughly 1/4, very similar to the exponents seen at the dangling edge. So perhaps the dangling edge is controlled by the special transition.
Sorry, can I ask a question? Sorry, for spin 1, they studied the same model with JD and J different, and so this power law behavior at the edge was observed at some transition point or in finite region?
All of this is at the bulk transition.
Okay. Yeah, then that makes sense. Yeah, thank you.
Yeah. So
maybe let me ask something more naive. I probably need a bit more help to relate this quantum model in two-dimensional space to the classical model you start with in three-dimensional space. The detail of maybe the coupling in the quantum model. I'm not sure I understand the roles that play by this.
Yeah, so time becomes J over J becomes like T, becomes like the temperature T in the classical model, right? So this is the parameter you tune across the bulk transition. Yeah.
Right.
Otherwise, essentially the same thing. I will come to the difference between spin 1/2 and spin equal 1 in just a second.
So let me make sure. JD over J is T or 1 over T. Which one?
Let's see. I think just T, right? Because the paramagnet is the large JD over J.
Okay. And then when you say this dangling edge or non-dangling edge, these are run in one system, or it's actually just two different setups. I just want to make sure when you draw this, just for the convenience, you put two types in one system, or actually
we are always when we are doing theory, we are always studying a half-infinite system, right? So imagine that the dangling edge, we have a half-infinite system stretching this way, and the non-dangling edge, we have the half-infinite system stretching this way. But you know, of course, in numerics, people always study finite systems. So yeah, did I answer your question, Giovanni?
But just make sure. But you extract this delta, the dimensions directly from one simulation, so you actually considering two different set of simulation.
Yeah, there are two different setups. In one setup, one takes both edges to be n, and in the other setup, one takes both edges to be d. But
Okay.
one always, yeah.
Right. Yeah, that answers my question. Thanks.
Other questions about setup? Yeah. So this is this is the current best guess is that perhaps this dangling edge is described by the special fixed point. In particular, the scaling dimensions of the boundary spin seems to match. The puzzle is that there are the special fixed point. You have to fine tune to be at the special fixed point. And in fact, in classical Monte-Carlo simulation, it's quite clear that you need to fine tune. In these quantum models, you have this dangling edge seemingly without fine tuning. You have all these different models with s equal 1/2, s equal 1. People also studied different geometries. Some of these papers had a geometry different from this rectangular lattice geometry, and all of them seem to see same dangling edge exponent without tuning anything on the edge. So this is the real puzzle, and to me it's still surprising. Perhaps it's an accident, and this accident might be helped by the fact that actually at the special transition for n equal 3, we know that the correlation length exponent nu is large. So that means that if you start close to the special fixed point, you might need to go to very large system size to see true infrared behavior. Yes, but anyway, so this is where things stand. Now there is one further comment is about difference between spin 1/2 and spin equal to 1, right? So do we expect actually that for spin 1/2 models and spin 1 models the dangling edge will be the same, or will it be different, or what? Well, for a one-dimensional chain, right, we know how to incorporate difference between spin equal 1/2 and spin 1. It comes in the form of a topological theta term in the nonlinear sigma model. And for spin 1/2, we have theta equal pi. For spin 1, we have theta essentially 0 modulo 2 pi. But we know that actually this theta term being topological, it doesn't appear in perturbation theory at any order. So in particular, the perturbative beta function for the coupling G is the same independent of theta. So that means that in the extraordinary log phase is there for both spin equal 1/2 and spin equal 1. In fact, the theta term only enters through this non-perturbative Skyrmion configurations, which are weight like this in the action. Now, if G, we know in the extraordinary phase flows to 0, so these Skyrmions presumably are suppressed in the extraordinary phase. Now, what about at the special transition? At the special transition, the coupling G is the fixed point coupling is finite. But if it's small, perhaps the Skyrmions are again suppressed, and in fact, one can kind of estimate the suppression factor, and it looks large. So maybe that's what's going on. Maybe that's why. Let's say that the dangling edge is controlled by the special transition for both spin 1/2 and spin 1. In principle, we expect small differences in exponents for spin 1/2 and spin 1 due to these non-perturbative Skyrmion effects, but perhaps they're just suppressed because the fixed point coupling G is small at the special transition for n equal 3. So that could be a story. Whether it's true or not is not quite clear. In this story, actually, there is another important operator that we know from one-dimensional chains, the valence bond solid operator. In the nonlinear sigma model, it corresponds to the Skyrmion density, just to the thing multiplying the theta term. And perturbatively, this Skyrmion density, the scaling dimension, does not renormalize, is equal to 2. So if this Skyrmion suppression story was right, then we should see at the dangling edge, we should see this VBS order parameter having scaling dimension equal to 2. For s equal 1/2, the scaling dimension seems to be somewhat below 2. So either the Skyrmions play a role for some correlation functions but not for others, or maybe something is wrong. So I think this is still quite open. Okay, so let me conclude this part of my talk by saying that boundary criticality, even in the simplest classical ON model, appear to still have some open questions. It would be great to settle these questions with more Monte-Carlo, both classical and quantum. Perhaps something can be learned about NC from conformal bootstrap. Yeah, and so this is kind of concludes the non-technical part of my talk. And then if people are interested,
before the technical part, just quick. So once again, just the big picture. You look at basically two-dimensional core function s of x, s of 0, and you explained, say that at n equals 2, it's 1 over log, and it goes to a power, at 1 over log, basically a critical point, and it goes to a power law at large distances if you are in the above the line, right?
Yeah.
Right. So when there is no order parameter. Now, just to make sure, so if you're slightly below the line, so that there is a bulk order parameter, but it's small, how the core function crosses over? It's logarithm and then it crosses over to what?
It goes to a constant at large separation, and this constant we should be able to actually calculate how it depends on the bulk correlation length. So it's probably like, yeah.
The scaling dimension of the bulk should probably matter somehow.
So there is again essentially a correlation length, or if you wish crossover length in the bulk, right? So I think if you just put this log c to q over 2, or log c to the q is what this correlation function will go to.
Okay, so it may be large compared to what is in the bulk.
It's large. So the bulk magnetization goes to 0 at power law, but this one actually goes very slowly.
Much slower, yes, yeah, that makes sense.
So it's almost like this picture that was people put forward in the old
right, yeah, that's why I'm asking.
It still goes to 0, but the slope is yeah.
Right. Okay, thanks. Yeah.
Yeah. So if people are interested, I can talk about some of the details of the RG, but also I don't want to exhaust the listeners. So if perhaps people who to leave, I don't know, or we can just stop here.
People can
up to the audience.
People can ask some question if they want now, and after that you can continue. Well, maybe one question for Max is that can you suggest some additional numerics for future works? More precisely, what would you suggest people to do?
Well, I think n equal 4 is interesting. I think n equal 4 is somewhere close to NC. So so that should be definitely studied with classical Monte-Carlo. For in the quantum models, really, I think people. Well, of course, you can always go to larger system sizes. This is always the dumb thing to tell to tell numerical people. But maybe it's actually better to try perturbing this dangling edge and see whether people can really push it to the ordinary or extraordinary log phase. People actually already tried perturbing, but maybe more general perturbations need to be considered. Yeah.
Maybe I have a related question. Maybe so theoretically we can change n as a continuous parameter, which I guess you did, Boris. But and people do talk about n goes to 0 limit even. But so from your result, it maybe like n equals to 4.5 or something could be interesting. But yeah, it's at least can be defined for the continuous value of n. The model can be defined in terms of high temperature expansion or something at least. But can we think some physical example corresponds to n equals to 4.5 or whatever fractional value of n?
Yeah, I think in terms of lattice models, I think these classical models can be reformulated as loop models typically, right? And I don't see why these loop models cannot be studied in the presence of a boundary, and then in these loop models n can really be made into a continuous variable. So I think that's actually quite interesting. But so far there is just so little work on these models. Even for integer values, people don't quite know yet what the phase diagram is.
Yeah, I agree. But so on the other hand, if you construct a transfer matrix for this ON model, maybe the Hamiltonian, or how to say, the transfer matrix is not deflection positive. The Hamiltonian is not Hermitian. Maybe I'm confused. Is there no problem at all to extend n to continuous value?
I think, well, yeah, good question. So of course, the thinking is that when n is not an integer, these are not unitary. Unitary models, but at the same time, somehow, if you formulate as a loop model, I think you still have weights. Maybe somehow, if you try to write it as a local model with positive weights, then it's difficult. Yeah, I'm not exactly sure. That's actually.
But you expect that this RG phase diagram evolves continuously.
I think. Well, yeah. I don't see. I don't see why not.
Yeah.
Although actually, in 2 dimensions, I think in 2 dimensions people have been studying this ON with n less than 2, and I think there are some puzzles there. With crossings models with loop models with crossings allowed and with crossings forbidden, and somehow they are in different universality classes. So there might be subtleties, but
okay, thank you.
So Max, you may continue, please.
Okay, so here is. Here's everything swept under the rug. So how do we describe this this RG? So here is the story. Again, remember, we want to start in the regime when the surface has strong coupling between spins, right? And we describe the surface by this ON nonlinear sigma model, and then we take the bulk. And initially, let's take the bulk with ordinary boundary conditions, right? So if you wish, imagine that the next layer away from the boundary, well, the next layer has the same coupling as the bulk coupling and is now in the ordinary universality class. And initially turn off the coupling between the boundary layer and the next layer, right? So then everything but the top layer is described by this boundary conformal field theory with ordinary boundary condition. Then the top layer is described by the nonlinear sigma model, and finally there is the coupling between the two. Here phi is really the phi of the ordinary boundary conformal field theory is really the boundary operator corresponding to phi. And we want to study the physics of this model in the infrared. And we want to study it in the regime when, first of all, G is small. So when G is small, essentially we expect that n should not fluctuate too much, and we can expand n around, say, the North Pole. And in fact, when g is strictly equal to 0, then n is completely frozen. In particular, let's say it points along the North Pole. So if n is frozen, then this is like the like a boundary magnetic field. Therefore, the system in the infrared will then flow to the normal universality class. So that will be the starting point in our analysis. This S tilde will be relevant and will flow to the normal universality class. Now, really, the reason that we can make progress is that we know a lot about the normal universality class. First of all, we know that for the normal universality class, again, remember, normal universality class means there is a symmetry breaking field on the boundary. First of all, the longitudinal component of the bulk field acquires an expectation value parameterized by this parameter a sigma here. And here I'm writing down the operator product expansion of the bulk fields near the boundary. So for the longitudinal field, there is this leading term, which is just a constant boundary operator, corresponding to an fact that phi is condensed on the boundary. And then there is a subleading operator here. And then for the transverse components of the field, of the bulk field, the ones perpendicular to the surface magnetic field, there is no expectation value, but there is some leading boundary operator here. So boundary operators are denoted with a hat, and bulk operators are denoted without hats, and we normalize operators in this way, such that both bulk operators and boundary operators are normalized to identity. Now, there are few things we know about these leading boundary operators. First of all, the transverse in the transverse channel, the leading boundary operator has a dimension equal to 2, exactly. When dimension d, bulk dimension d is equal to 3, this scaling dimension is exactly equal to 2. It's a protected operator related to the current, actually, current in the bulk, or n current in the bulk. And then sigma hat is again a protected operator, is what people call a displacement operator. It's related to the stress energy tensor in the bulk, and sigma has scaling dimension equal to 3 exactly again. So these are the most important facts. Okay, so when g is equal to 0 and n is not allowed to fluctuate, we know that the boundary flows to the normal fixed. What is the leading perturbation point that we induce? And well, the simplest coupling that we can write down is a coupling between this transverse component of n, pi, and the boundary operator of the normal fixed point, the transverse operator. This turns out to be a marginal coupling, as we will discuss in a second, right? Phi hat has dimension 2. At g equals 0 fixed point, pi has dimension 0, so this is marginal. Interestingly, we started with this action in the UV, which was ON invariant, but this action in the IR is seemingly only has ON minus 1 invariance, right? Because we kind of started by breaking the symmetry by picking n to point along the North Pole. If you try to, and in particular here we are coupling only the transverse components of n and the bulk field phi. What if you try to couple longitudinal components? Well, you'll induce a coupling like this, but sigma hat has dimension 3, so this would be an irrelevant coupling. So that means that this is the only marginal coupling we can write down. And furthermore, so it means that somehow this has to have a hidden ON symmetry, even though only ON minus 1 is manifest. And in fact, my claim is that if you start here in the UV and flow to the IR, you will end up with a very particular value of S, one that respects ON symmetry, and which is given by this ratio of the universal amplitudes at the normal fixed point, A sigma and mu phi. How to see that? Well, still keeping n as a constant vector, when n points along the North Pole, the bulk order parameter also points along the North Pole. Here is how it looks. Now let's imagine that we rotate n slightly away from the North Pole, right? So we allow for a small constant value of pi. Then in the bulk, we should acquire a transverse component of the order parameter proportional to pi in precisely this manner. But I can also try to describe this using perturbation theory in pi, using this coupling. Here is to first order in pi what the result would be, and this 2-point function with one field in the bulk and one field on the boundary is fixed exactly by conformal invariance. It's given by this. So if you put this into the integral, do the integral, you obtain exactly this relation. S is given by this ratio, amplitude ratio, right? So S is a universal number. This is the most important point. S is not a free parameter. It's fixed precisely by ON symmetry. The only free parameter is the coupling constant G in the nonlinear sigma model. S is not a free parameter. What is the value of S? Well, really, we need these amplitudes at the normal fixed point. One can obtain them in the Lagrangian expansion. So here is the result to the non-leading accuracy. It took me like a week to calculate this subleading correction. But really, the calculation is based on an old paper by Ono and Okabe. One can also try to obtain them in 4 minus epsilon expansion, but at least for a squared sigma, that seems to give very unreliable results. Like you get a squared sigma, which is negative if you try to put in epsilon equal to 1. So yeah, I think for moderate values of n, these numbers are still up in the air. We don't quite know. Anyway, so now we know the full action of the theory, and we can proceed with the RG analysis, right? So we do RG analysis just as we do it for the nonlinear sigma model. There is this coupling G. We want to understand how it runs. There is a contribution to running coming from this vertical interaction nonlinear sigma model. This gives this n-2 term in alpha, but there is an extra contribution from this coupling to the bulk fields, and it's very easy to calculate the diagram corresponding to this contribution. This is the diagram. You just kind of exchange a bulk phi field between the pi's, and you get this precisely this contribution to the RG flow of G, this pi s squared, right, with S that we discussed. The to this order, the anomalous dimension of n is not modified from what you get just in the nonlinear sigma model. No bulk contribution. So that's it. This is the RG analysis. Now, if you are skeptical about this RG analysis, there is actually a very non-trivial check on it, which is that so far we did the analysis in
Max, I'm sorry, but in this, this is a kind of trivial part of this RG analysis. That G is running itself, right? So there is a scale. So when you're saying that this is fixed constant, essentially it's not. It's a scale lambda which essentially fixed if it would be normal sigma model, right? You mean just consider this two-dimensional model in Polякov sense, right? I mean, in original, right? Then essentially you are trading off G for lambda, right? Lambda, I mean, its scale.
Well, in that case, it's common practice, right? So in that case, this this alpha is negative, and
I see. Okay.
you just finite correlation length, and it's standard practice to trade G for this finite correlation length, so you have a dimensional transmutation.
Yeah,
right?
But it is always scale, right? So it's infrared scale or UV scale, right? That's it. That's the difference only.
One is correlation length, another is like a crossover scale. So in principle, you could trade G for some crossover some scale. Yeah, it's no difference really.
Yeah. Okay.
But this is, you know, this alpha G squared is the beta function. This is what we want to ultimately compute. Yeah. So you might, you know, I was initially skeptical of my own analysis, but there is a very non-trivial check on this analysis, which is that you can repeat the same analysis when dimension is just slightly above 3 dimensions. Above 3 dimensions, we know we have a special fixed point. No question about that. We have the extraordinary fixed point and we have the special fixed point. And moreover, for large n, we know the scaling dimensions at the special fixed point. So we can compare to this RG analysis when dimension is just slightly larger than 3. So how is the RG analysis modified when dimension is slightly larger than 3? We have this extra minus epsilon g in the beta function, right? So now g equals 0 is a stable fixed point. This is the extraordinary fixed point. At this fixed point, fluctuations of n really decouple. You really have, it's really essentially the same as the normal universality class. You can kind of think of n as frozen along say the North Pole. So that's the extraordinary fixed point. And then the special fixed point at small epsilon sits at this value of coupling constant, epsilon over alpha. So you can, this is assuming that that n is greater than nc and alpha is negative. So then, you know, when epsilon is small, this is a small number, so the scaling dimension is also small, and we can, because we know alpha in the large n limit, we can calculate the scaling dimension at the special fixed point in 3 plus epsilon dimensions in the large n limit. This is what you get. And then you can compare this to the result of Ono and Akaba, which is done just by turning the 1 over n crank. Very, very different calculation, but you get the same result, including the 1 over n correction. So I think that's really quite a convincing demonstration that this RG method works. I think this is what I had to say. Any remaining questions?
Maybe I missed a point. Sorry. What's the non-trivial statement about the RG for the confirmation to rule out your skeptics earlier? What's the
Well, so there is a check, right? You can apply this RG in dimension 3 plus epsilon. Above n equal nc, you find a infrared unstable fixed point at a finite value of g, small finite value of g. You can calculate the scaling dimension of the order parameter at that fixed point, and then you can compare to 1 over n calculations that are done at the special fixed point in general dimension, and then take dimension to 3. So very different calculation techniques. One is RG analysis that I've described. Another is a kind of brute force 1 over n calculation in dimension d greater than 3, extrapolated, and you take the answer and extrapolate it to d equal 3 plus epsilon, and you compare. Right, so it's comparison of RG and 1 over n in a regime when d is equal to 3 plus epsilon and n is large, and they agree. Yeah, this is the check.
just mention one is epsilon expansion, the other is 1 over n. Or no?
One is
Actually,
one is this unusual epsilon expansion, right? So it's not 4 minus epsilon, it's 3 plus epsilon.
right.
And it's really based on the RG analysis that I presented in when epsilon is equal to 0. It's a small modification of that RG analysis.
Thanks. Thank you. So maybe people can continue to ask questions. Just make sure. So here you have a maybe more like a target space, target manifolds like OM, right? What do you think will be the case if you consider other type of nonlinear sigma models with different target space? Do you expect some behaviors for the criticality you can also say?
Good question, but you have to decide what the bulk theory will be then, right? So we have to have some kind of bulk phase transition, and
Okay.
I'm not sure we know the universality classes of those bulk phase transitions. Yeah. Other questions?
Do people, maybe this is a naive question, and I think Masaki has a question further. Do people know the bulk criticality for other type of a sigma model with maybe some Grassmannian manifold or steeple manifold type of a like quotient space of various Lie groups? Are these known in the literature? I'm not sure. I just ask.
Yeah. Sometimes you can write down like in the naive Landau-Ginzburg theories, you can write down cubic terms in some of those models, and so kind of people sometimes think maybe they're first order transitions, but I think this is kind of lame. Probably just means we don't know what the continuum, what a continuous transition looks like. I don't know if Masaki has a better answer. Yeah, for some of them, maybe we can write them down as some kind of gauge theories, reformulate them as gauge theories, like a CPN model. Yeah, that's a whole other class of questions. Like in say CPN model at large n or moderate n.
Masaki, you have a question, right?
Okay. So maybe you already discussed, but this extraordinary surface critical behavior, can you relate to some long-range interaction model? Because the bulk kind of mediates the longer range interaction in some sense, I guess.
Yeah, that's a good question. Somehow, the nice thing about this model is that everything is local, right? Strictly speaking, all the interactions are local. In the long range models, somehow it would be more natural to just have true long range order in the infrared, to have this situation where the power law, where the correlation function decays as a power of logarithm, seems very fine-tuned, I think, from that perspective. But Yeah, I'm not sure. In fact, some of the models with long-range interactions that Chenke and collaborators have discussed, in fact, do have this extraordinary phase with true long-range order.
Yeah, thank you.
Any more questions from the audience? Feel free, please. If not, let us thank Professor Max Metlitski again for the wonderful seminar. Thank you very much. And people have more questions can still stay to ask. Thank you. Thanks very much.
Till then.